All right, so just a reminder of where we're at. Today we're talking about the binomial theorem. Wednesday, we're going to do fun problems. And so that'll be just like a group work day. Come and wrestle with. I'll give you a bunch of them. And then no class on Friday. Next Monday, we will review. And then next Wednesday, we will have the exam. So I will have information about the exam by Wednesday. I will also have your homework to give back by Wednesday. All right.
More than one.
More than one homework. So I took homework 6, and then homework 7 will be due the class day after the exam. Okay. All right, so just to remind you, let me put a divider here. Last time we talked about these equations, permutations and combinations. So permutation and combination, where a permutation is the number of sequences you're trying to order a certain group, and the order matters in a permutation. And the equation, so I'll put a star next to the word order, and the equation for that is, oh my gosh, I'm forgetting it off the top of my head. I know the one for combination. Combination order does not matter. This is a list of subsets. And so this is n factorial over n minus k factorial times k factorial, which means the permutation is just n minus k factorial, which is because in permutation, the order matters. And so if we have n permutation, like we're trying to find k element permutations from a set of n things. And so there's all these different ways to order it. So if we have each subset, there's k different ways to order a subset of length k, right? For combinations, we don't care about the order of the subset. And so that's why we divide by the k factorial. And so we write this NCR, or also C and no, not R, K. So that's how we write that. I want to briefly discuss problem B on this one of your homework problems, which is if we are considering dice rolls of 6 different dice, so we color each dice just to make them distinct. And the question is, how many different rolls have at least one, number 1, appear among the 6 dice? And so the question is, why is it 6 to the 6 minus 5 to the 6 versus 1 times 6 to the 5? And so the reason here is that the key word in this problem is at least, where for this one, we can fix the first one as a 1, and we can have every other dice be whatever we want. But we want to capture at least 1, 1. And so for that reason, when we have something that like at least or at most, then that's a hint that we're going to have to use the complement rule. And so for that reason, all the possibilities, so no restrictions on what the number is, that's 6 to the 6th. Right? So we've got 6 dice, we can roll it however we want. And there's 6 options, so there's 6 options for each die, and we've got 6 dice. Right. The other option is that so the complement rule is anything but what we want. And so if we want a 1, then the complement of that is that there's no 1s, right? 1 is disallowed. And so from that, we've got 6 dice, but only 5 options are allowed. And so by the complement rule, we end up subtracting the complement, which is we have 6 dice, but only 5 options are allowed. And so this captures more accurately all of the possibilities. So for at least one, because there's a possibility that like all of them are 1 or that 5 of them are 1. And so this captures that better and more fully than just 1 times 6 to the 5th. Does that make sense? Okay. All right, so I've got a warm up for you. And this is a problem I ran into yesterday. So I have a gig up at a church, and on Sunday mornings I go and help out with AV. And so this includes running the soundboard, running the slides for like the words to the songs, or running the cameras because we live stream it. And so these are 3 separate jobs. And I'm kind of the volunteer manager. And so I've got 5 different people, including myself, who can be available to work these 3 jobs. And so the question I had yesterday as I was getting ready is I've got 5 people available, but only 3 jobs. So that should be a 3 instead. And 3. And so I would like to know how many 3-person configurations are there if the positions matter. So I'm going to assign 1 person to sound, 1 person to slides, 1 person to camera. Or if the positions don't matter, where I'm just like, you 3 people, you are running the service, and you 2 people are not. And then I would like to know, so these are the initials of the people involved, but just the first initials. And so what are the combinations of all of these people? So if we know how many there are, then write out the combinations. And for this, I really mean 5, choose 3. So write out the combinations and not the permutations, because there's a lot more. So that's the first question. The second question is, I've got these polynomials, and I would like you to expand them. All right, so I will pause recording, and I've got markers, so get into groups, go to the board, talk about it. All right, so let's take the case for my AV problem. So 5 permute 3 is 60. And then 5 choose 3 is 10. And so we can write all of the options as, okay, I'm going to write these out. Let me know as I go if I have made a mistake. One, two, three, four, five, 6, 7, 8, 9, 10. Good. Great. So those are all the possible combinations. So we're going to talk about a theorem. This theorem is the binomial theorem. This comes from section 8.4 in the textbook. And this theorem says for integers n and k, and we'll restrict k to being between 1 and n. We have the following equation. C of n and k. So n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Hooray. Those are numbers and letters. Let's talk about what that actually means. So there are 10 different subsets to assign 3 people to running AV or not running AV, right? So there's 10 of these total. And so let's consider configurations where I'm working versus I'm not working. And so all of these on the left, there's 6 configurations where I'm working, 4 where I'm not. And so, and this is going to be true no matter who we choose, right? So let's just choose me. We can partition this list of subsets into 2 separate groups. One of which is where I'm working. The other is where I am not working, right? Partition. Remember, what was the rule where we talked about partitioning? Think about that for a second. We talked about this, so way back when we started this unit, we had 2 rules, right? We have multiplication rule, and we have the addition rule, right? And so the addition rule is all about these, like, what was it? Like distinct, pairwise distinct subsets, right? Where we can like divide them. And so this is where we've partitioned the set into 2. All right, and so how many have me in them? 1, 2, 3, 4, 5, 6. How many don't? 1, 2, 3, 4. Great, those are numbers. Let's write them in terms of combinations. So we know that 5 choose 3 is 10. So let's subtract 1 from n and k and see what the different possibilities are. So if we subtract 1 from n, we have 4 choose 3. That's a number. If we have 5 choose 2, that's another number. If we have 4 choose 2, that's another number. Right? So I'm subtracting 1 from n, 1 from k. So either or 1 from both. So take a second and talk with your neighbor. What are these values? So I would like the actual value. Like 5 choose 3 is 10. Go for it.
That's was
All right, getting close. It doesn't help that my pen is white and the pages of the textbook are also white.
Yeah.
Very inconvenient.
Discipline. Wait, show me the equation. What's up?
Wait, like these guys?
There's the one that's like, yes, okay. C n minus one, choose of n minus one, k plus n minus one, k minus one. It's equal to n k.
Yeah. So we're doing like a proof by example to demonstrate this theorem. So what's 4 choose 3? 4. What's 5 choose 2? Wait, say that again. 10. What's 4 choose 2? Which ones match to the numbers that we have? Yeah. 4 choose 3, 4 choose 2. And so this is our proof by example, where if we want to find out C of nk, so let's rewrite this equation. Let's write it in the shorter format. So nck is equal to n minus 1 ck plus n minus 1 c of k minus 1. And we see this where we have 5 choose 3 is equal to the number of combinations with me in it, which is 4 choose 2 plus 4 choose 3. Right? So these numbers match up. And I will note that so I stared at this theorem definition for a long time this morning because I was like, we're not choosing subsets of 2 from 4 people, but the numbers do match up, right? So this is 4 choose 2 is 6, and then 4 choose 3 is 4. And so adding those numbers together, we get the number of combinations to choose 3 people out of 5. All right, so that's the binomial theorem. You can also prove this algebraically. So if we write this as n factorial over n minus k factorial times k factorial, we can prove that this is equal to n minus 1 factorial over k factorial times n minus 1 minus k plus same numerator over k minus 1. So that just gets that. And then n minus 1 minus k minus 1 factorial, right? We can prove this algebraically. We won't do this in class, but you can do it. This is number 6 of 8.4, in case you're interested. All right, so that's the first activity that I made you do. The other activity is I made you expand all of these polynomials. So a plus b to the 0th is just 1. A plus b to the 1 is just a plus b. Just for kicks, I'm going to put a 1 there. It's implied, but it's still there. A plus B squared is what? A squared plus 2AB plus B squared. So I'm going to write a 1 there and a 1 there. A plus B cubed is, would someone like to read it to me?
Plus 3AB and B, or sorry, it's 3A squared plus 3 A and B squared plus B cubed.
All right, thank you. And we can go on. We can do A plus B to the 4th, A plus B to the 5th, so on and so forth. And so this is going to give us something that we call, so we're looking at these numbers. So like we're looking at the 1, that's a 1, that's a 1, 1, 2, 1, 1, 3, 3, 1. And the term for these numbers is coefficients, right? This is the number that gets multiplied by the term. And so we can write this in the form of a triangle. Nope, that's not correct. That's a 2. That's a 1. And then we have 1, 3, 3, 1. The way we get, so let's say we've got two numbers x and y. The way if we draw it like this, there's going to be, so we've got 1s going down the sides. And so the way we get a number in the middle is if we've got two numbers above it, the number in the middle is going to be x plus, like 1 plus the other. And so we've got a 1 down the side. And so the number here is 1 plus 3, which is 4. The number here is 3 plus 3, which is 6. The number here is 3 plus 1, which is 4. And then we've got the 1 at the end. So we can expand this table as we go. This is called Pascal's triangle. And it's super cool. It has a bunch of applications, one of which is that when we are looking for, like, let's say we want to expand out a polynomial, we've got another binomial theorem. This is the actual binomial theorem, because if we have a plus b to the n, that's a plus b, that's a binomial, and we are raising it to the power of something. And so we have a plus b to the n is equal to, and here we just want to write out the coefficients of that row of Pascal's triangle. And so this is for n equals 0, n equals 1. This is n equals 2, n equals 3, n equals 4, and so on. And the other nice thing about this triangle is that, let's consider, so we're going to hold off for a second on completing this theorem. I'm going to go back over here. Where did you go? Here you went. Cut. Okay. So what's 0 choose 0? 1. What's okay, what's 1 choose 0? What's 1 choose 1? What's 2 choose 0? Also 1. What's 2 choose 1? What's 2 choose 2? Right, there's one way to choose 2 things from a set of 2. Okay, we're gonna do one more round of this. What's 3 choose 0? What's 3 choose 1? What's 3 choose 2? What's 3 choose 3? Do these numbers look familiar? Okay, let's paste this. Where am I gonna put it? Okay, let's move this over here. Make it bigger. So these numbers like 0 choose 0, 1 choose 0, that's Pascal's triangle. And so the rows are values of n, and the quote unquote columns are values of k. And so that's n, and then that's k as we go along. And so initially we only, since k is limited by n, we start at 0, and then n is 1, and so k is either 0 or 1. If n is 5, k is either 0, 1, 2, 3, 4, or 5. Right? So computing combinations gives us all these possible combinations, gives us Pascal's triangle. And so with that, now we can finish this equation. And so each term, so like if I'm looking at a plus b to the cubed, and I'm looking at like, what's this term? So I want to count, so this is for k equals 0, k equals 1, k equals 2, k equals 3. For n equal to 3. And so for each term, to find out the coefficient, I'm going to write n choose k. And I'll just tell you that if we're writing a plus b, the exponent on a is going to be n minus k. The exponent on b is going to be k. And to get the whole polynomial, we just stick this thing. So this is for each individual term. To get the whole polynomial, we stick it in a summation. So we start from k at 0, and we go up to n. All right, we won't prove this, but this is important to know of like what this means. So we get so a times b are multiplied together, and the coefficient is just n choose k, which we see in Pascal's triangle. And so inside the summation, that's just one individual term. And then to get the whole expression, we put it inside a summation. And so we have the k equals 0th term, k equals 1th term, 2, 3, and so on, up to n. Okay, questions? All right. So now I have a problem for you, or multiple problems. So I've got 3 questions for you. The first is a woman has 6 friends. Each evening for 5 consecutive days, she invites 3 of them over for dinner in such a way that the same group is never invited twice. So how many ways are there to do this? Assuming that the order in which you invite groups, so like I'm inviting this group on the first day, this group on the second day, on the third, and so on. So the order invited matters, but the makeup of the group does not matter. So that's one of the questions. The other one is we've got a piece of music and it has 4 beats in a measure. And we've got different kinds of notes. So we've got a 1/8 note, that's half a beat. We've got a quarter note, that's just 1 beat. We've got a half note, which is 2 beats. And a whole note is 4 beats. And so let's say I have a measure and I want to know how many different rhythms can I fit there. So for example, I can have a 1/8 note, a quarter note, an 1/8 note, and a half note. Another, I could have a half note and 2 quarter notes. Another is I can just have a whole note just for the whole measure. Another is I can have 4 quarter notes. All right. So this is a music question. And they say math isn't artistic. And then the other one is I've got 7 computer users that are trying to establish a connection with 5 networks, and not all of the attempts to connect are successful. And so how many successful connections can be established? And how many configurations does each computer user establish a wire connection with? Exactly 1 wireless network, at least 1, or at most 1. Okay, these are tricky problems. So I think I might put you in different groups and then we can work on them for the last 15 minutes of class.